On September 6, 1943, an initiating failure sequence isolated a heavy bomber over hostile territory. Weather delays shaped the wider Stuttgart mission, but the specific loss sequence for Lucky 13 began with flak damage in the right wing, a severe fuel leak, separation from formation, and then interception by a Focke-Wulf 190 before the crew abandoned the bomber. The machine caught in this irreversible operational deficit was a Douglas-built Boeing B-17F-65DL Flying Fortress, serial 42-3455, commonly identified by its crew as Lucky 13, assigned to the 384th Bombardment Group, 546th Bombardment Squadron. This bomber ultimately fell 14 miles east of Beauvais, France. For decades, the physical remnants of the bomber lay scattered across the forest floor. The site experienced extensive localized scavenging and environmental degradation. The primary fuselage structure was obliterated, leaving only isolated fragments of aerospace aluminum, scattered brackets, and torn framing buried in the soil. In any forensic aviation investigation, the passage of time radically alters the baseline condition of the evidence. When researchers finally excavated the remaining original artifacts from the crash site, they did not find a reconstructable airframe. They found a shattered debris field. Aviation archaeology does not begin with romance, it begins with traceability. The fragments recovered 14 miles east of Beauvais had to be correlated with the documented crash location, the missing aircrew report, unit records, crew testimony, and the known identity of B-17F serial 42-3455 before they could anchor the modern recovery operation. The Hangar 13 Foundation, led by Ray Moore, initiated a massive project to rebuild this exact aircraft as a combat memorial. To achieve this, the operation relies on a rigid forensic concept known as provenance transfer. Provenance in this rebuild is not a magical legal mechanism. It is the documented chain that ties recovered material, photographs, records, and ownership history back to a known wartime loss. In the standard aviation framework, an aircraft identity is handled through identification data, records, registration, and repair status, not by an abstract transfer from scattered metal. The excavated artifacts connect the rebuild to serial 42-3455 and keep the project from becoming a generic B-17 representation, but they do not, by themselves, prove every legal status of the completed airframe. The operation is bound by this initial condition. However, securing the historical association only clarifies the engineering problem. The team must build a structurally viable airframe from verified Lucky 13 material, donor B-17s, and scratch-built structure formed from original drawings and modern reference work. Because the French site fragments remain evidentiary and geometric rather than load-bearing, each original piece must be evaluated for preservation, scanning, display, reference, or safe incorporation. Pieces that retain useful geometry can guide the shape of new work. Pieces that are too distorted, torn, or weakened by impact forces and corrosion must serve as evidence, reference, or templates, rather than primary load-bearing structure. The central procedural question remains entirely structural. How does a shattered, decentralized debris field physically map to a structurally viable composite airframe? When a heavy bomber depletes its energy reserves, the operational trade-off narrows to a single irreversible decision. 10 crew members must evaluate the failure state of their machine and abandon the airframe to secure their survival. For the personnel aboard this specific aircraft, that failure sequence narrowed into a survival problem. 3 crew members are reported as having evaded capture: Falconer, Hawes, and Hamblin. 7 others became prisoners of war. But before that human outcome, they had to execute a procedural exit from the failing aircraft. The decision to evacuate is forced by a rigid mechanical process known as the fuel depletion cascade. The operational constraint is absolute because the aircraft lacked the chemical energy required to reach a safe landing zone. Excessive loiter time and increased aerodynamic drag from flak damage forced the fuel consumption curve of a bomber past the point of safe return. The engines can no longer convert liquid mass into thrust, causing the airframe to lose its forward energy. Without thrust, altitude cannot be maintained, forcing a direct trade of altitude for airspeed. The flight profile degrades into a terminal descent. The pilot ordered an immediate bailout, all 10 crew members successfully abandoned the bomber while it still retained enough altitude for parachute deployment. The trade-off edge was sharp, requiring the crew to evaluate the altitude loss rate against the time necessary for 10 men to physically clear the escape hatches. Before jumping, Falkiner activated the autopilot, leaving the aircraft unmanned, but not instantly uncontrolled. From that point forward, no pilot remained aboard to manage a landing, flare the aircraft, or protect the airframe from the terrain of the French countryside. The resulting outcome was defined by unpiloted impact geometry. The dense timber of the forest presented an immovable physical boundary against the moving airframe. An abandoned gliding heavy bomber impacting a dense forest undergoes rapid kinetic disassembly. The forward momentum and vertical descent rate convert into extreme destructive force upon contact with the tree canopy and solid earth. The load paths within the airframe cannot absorb this massive sudden deceleration, causing the fuselage to shatter along its primary structural frames and shear heavy components from their mounts. The forest created a highly specific set of forensic hazards for aerospace aluminum. Dense vegetation traps moisture directly against the torn metal surfaces. Soil acidity and continuous organic decay initiate a slow, relentless oxidation process that attacks the thin gauge materials. Over several decades, the unprotected structural components degraded significantly. Where pieces had been removed, investigators also lost portions of the debris field's original geometric context. When researchers finally assessed the remnants, they operated under severe physical limitations. The remaining artifacts were bent, sheared, and structurally compromised by the extreme violence of the impact. The long-term environmental exposure had severely weakened the original alloys. The operation became a fragment extraction rather than a section recovery. They could only extract shattered fragments of a destroyed machine from the root systems of the forest. The archaeological extraction required careful digging to free the remaining aluminum from decades of soil accumulation without causing further structural tearing. This environmental and kinetic reality pushes the rebuild into its next structural stage, using surviving F model evidence to govern geometry, while heavy, intact donor bulkheads from later G model aircraft supply the strength missing from the crash site. This structural marriage relies on a highly specific engineering framework known as composite architecture. Composite architecture is the controlled integration of isolated original artifacts, heavy donor fuselage sections, and newly fabricated sheet metal into a single coherent load-bearing airframe. In a heavy bomber, the fuselage relies on a semi-monocoque design where the internal frames, heavy bulkheads, and exterior aluminum skin all share the physical loads. Because the original forest salvaged metal is heavily compromised by kinetic trauma and decades of corrosion, it cannot safely carry these operational stresses. Therefore, the intact G model donor bulkheads must serve as the primary foundational strength of the new structural assembly. Historical identity alone does not supply the missing dimensions between the parts. The engineering team must physically connect surviving F model evidence, donor B-17 components, and newly fabricated structure, and they cannot rely on visual estimation to span these missing sections. To solve this strict dimensional problem, the operation uses original drawings where available, wartime references, restored components, jig assemblies, surviving wreckage, and modern scanning when drawings no longer exist. These references provide the baseline required to recreate missing 1943 structures. Cross-referencing surviving fragments against drawings, scans, and known B-17 assemblies lets engineers verify the Douglas production standard without pretending that every drawing survives in one complete archive. Where the wreckage can no longer supply dependable shape, the drawings and scans guide new aerospace aluminum to match the original configuration as closely as the evidence allows. On the hangar floor, that evidence-driven workflow dictates the formation of new skin panels, structural stringers, and internal support bracketry from scratch, all aligned with the donor structure and the project's jigs. The operational constraint is dimensional discipline. If newly fabricated sheet metal deviates from the reference geometry by even a fraction of an inch, the load paths will not align, and the fuselage structural splices will fail to join correctly during final assembly. The result is slow work by design. The original F model components dictate the specific geometric shape of the aircraft, while the G model bulkheads provide the necessary structural volume to support that shape. The newly formed sheet metal, guided by the original microfilm, serves as the physical bridge locking these two disparate elements together into a solid cylinder. This integration restores the bomber's volumetric shape and continuous load-bearing capacity. However, integrating massive donor sections from a later production variant introduces a new boundary defined by the physical evidence built into the parts themselves. To construct a 1943 B-17F, the engineering team must adapt whatever usable B-17 material is available to the specific configuration of Lucky 13. Later B-17G aircraft did introduce major visible changes, including the powered chin turret used for head-on defense, but the public record does not confirm that Lucky 13's current donor structure requires the exact nose modification removal sequence described here. The safer engineering reality is broader and still severe. Every donor component has to be checked against the correct F-model geometry before it can be allowed to define the final shape. That check begins at the level of frames, brackets, and attachment points because those features dictate the final external and internal shape of the aircraft. Incompatible wartime or post-war alterations can shift the landing points for newly fabricated exterior skin, interior fittings, and system brackets. So the team strips, measures, repairs, and refits donor material only as far as the evidence and drawing support. Executing this retrofit requires extreme dimensional discipline. The engineers cannot treat vintage aluminum as disposable stock. Any removed bracket, rivet line, or reinforcement has to be evaluated against the surrounding structure. Where unwanted holes or altered attachments remain, the work must restore structural continuity without pretending that every donor component began life as part of Lucky 13. Once donor structures are stabilized, fabrication of early model framing can continue around the features that distinguish the F model interior: crew station supports, bomb bay details, and equipment mounts recreated from drawings, surviving components, and reference assemblies. That work brings the fuselage back toward the correct 1943 silhouette without overclaiming a named factory procedure. The donor work solves the primary fuselage shape, but the restored internal structures now demand specific early war equipment to fill the newly framed crew stations. When the team attempts to integrate surviving salvage hardware into these highly specific spaces, they face a new mechanical boundary. What happens when rare original hardware simply cannot be found in usable condition? For the ball turret installation, the lower fuselage requires the correct Sperry Type A-2 system used on B-17s. The boundary is not a confirmed 20-point versus 14-point bolt mismatch, but the scarcity of correct Type A-2 components and the absence of a usable original ball shell. Mounting incompatibility is the physical limitation that prevents the direct installation of whatever salvage assembly happens to be available into a specific, mathematically rigid airframe structure. In this instance, the correct interface is the B-17's Type A-2 ball turret hanger, trunnion, support structure, and shell. The related Type A-13 was built for consolidated aircraft and used a different hangar arrangement because the B-24 required a retractable turret for ground clearance. For Lucky 13, the objective is not to force a generic Liberator turret into place. The objective is to restore or recreate the correct B-17 Type A-2 installation. This scarcity creates an absolute physical barrier. The turret's mass has to transfer safely into the airframe through the correct load path. The team cannot compromise the newly restored aircraft structure merely to accept the wrong surviving hardware, or assume that incomplete parts become safe simply because they are old. Faced with this mechanical limit, the engineering team acquired and restored correct Type A-2 trunnion and hanger components where possible. Because the original ball shell drawings are long gone, the team had a surviving early ball turret scanned in 3 dimensions so the shell could be reverse engineered, molded, and eventually cast anew. That decision turns one localized assembly into a full manufacturing job. Scanned data becomes tooling, tooling becomes a cast shell, and the finished component must mate with the restored drive hardware and surrounding airframe structure. The finished installation must function as an accurate educational display and structurally belong in the B-17 rebuild. The trade-off is costly but decisive. It restores mechanical and historical coherence to the turret bay without forcing incorrect hardware into the lower fuselage. With that heavy interface resolved, the rebuild moves beyond structural hardware into the operational fidelity of the interior crew spaces. Before its destruction, this specific bomber completed exactly 7 combat missions, locking its baseline configuration to the tactical and manufacturing standards of late 1943. With the external aluminum skin aligned and the major hardware interfaces resolved, the engineering focus shifts inward. This final phase is governed by memorial conservation. The enclosed crew spaces must reflect the material reality experienced by the 10 crew members, down to the surfaces, textures, and functional components of the 1943 production standard. Enforcing this mandate creates a severe procurement constraint. The internal surfaces of early war bombers used specific acoustic and thermal barriers that are almost absent from modern aerospace supply chains. The unpressurized fuselage of a high-altitude bomber offered little protection from sub-zero atmospheric temperatures. To mitigate this hazard, specific crew stations used a cotton, kapok, and animal hair batting, known to Hangar 13 as sky-felt Quilco insulation. The material is extraordinarily rare, and Hangar 13 states that it does not exist on any surviving B-17 at this time. But it is not physically impossible to find. In 2022, the project received 2 bolts of aircraft insulation from the Hendry family, giving the team original material for reference and use. For the interior completion, the team could install a modern, visually similar aerospace substitute to accelerate final assembly and reduce fabrication costs. But modern synthetics would break the material accuracy of the crew compartments, so the restorers treated the surviving sky-felt Quilco as an original resource and pattern standard. The donated material gave the project a major step toward ultimate accuracy, especially in the nose compartment where diamond stitching was used across tight curves. The restorers must still distinguish between that nose insulation and the more common tube-stitched insulation used elsewhere, using the original material to define texture, thickness, stitching, and installation method, while future work addresses the other insulation styles and outer fabric layers. This discipline keeps the nose insulation, tube-stitched insulation, and outer fabric layers separated as distinct restoration problems rather than treating interior fabric as a single generic finish. Completed insulation becomes the final layer between structural mechanics and the human space of the aircraft, closing the interior volume around the rebuilt frames, bulkheads, cast brackets, and stitched panels. Upon completion, the foundation states that Lucky 13 will be the sole surviving aircraft associated with the Schweinfurt, Regensburg, and Stuttgart campaigns of autumn 1943. That distinction matters because other B-17F survivors still exist, but they do not carry this exact campaign history. That campaign-specific association is the final historical claim the completed memorial is built to hold.